Ever wondered how those massive engines propel airplanes across oceans? Today, we're diving headfirst into an exploration of the heart of aviation, the jet engine. These marvels of modern engineering, with their roaring power and intricate mechanisms, are the cornerstone of our ability to traverse the skies. We'll be delving into the basics of jet propulsion, introducing you to the thrust-producing phenomenon that underpins these engines. We'll also explore the different types of jet engines, from turbojets and turbofans to ramjets and scramjets, each with its unique features and applications. We'll also journey back in time to meet the pioneers who laid the groundwork for these technological wonders. And finally, we'll look to the future, considering the exciting advancements on the horizon in the world of jet propulsion. So, buckle up as we take off into the fascinating world of jet propulsion. Jet propulsion, a concept that seems complex, is based on a simple physical principle. At its core, jet propulsion operates on the principle of action and reaction, which is Newton's third law of motion. This law states that for every action, there is an equal and opposite reaction. In the context of jet engines, the action is the ejection of a high-speed jet of heated gas, typically air, out the back of the engine. The reaction, then, is the forward thrust that propels the aircraft. Now, let's talk about the different types of jet engines that are out there. First up, we have turbojets. These are the simplest form of jet engine, with air drawn in at the front, compressed, mixed with fuel, ignited, and then expelled out the back to produce thrust. Next, we have turbofans. These are a bit more complex. They come with an additional fan at the front, which not only helps with the compression of the incoming air, but also bypasses some of the air around the engine's core. This makes turbofans more fuel efficient and quieter than turbojets. Then, there are ramjets. These engines have no moving parts and instead rely on the speed of the aircraft to compress the incoming air before combustion. Because of this, ramjets can't start from a standstill. They need to be already moving at high speed. Lastly, we have scramjets, or supersonic combustion ramjets. These are similar to ramjets, but they operate at supersonic air speeds, with the air coming in the front of the engine and the fuel burning at supersonic speeds. This gives scramjets the potential for incredibly high top speeds. So, with a basic understanding of jet propulsion, let's delve into the heart of these engines. Turbojet engines, the pioneers of jet propulsion, are the backbone of many aircraft today. These marvels of engineering are intricate machines that rely on a fundamental principle: the Brayton cycle. This cycle, named after the American engineer George Brayton, consists of 4 main stages: air intake, compression, combustion, and exhaust. Let's break it down a bit. First, air is drawn into the engine. This air is then compressed by a component aptly named the compressor. This compression increases the pressure and decreases the volume of the air, preparing it for the next stage. Following compression, the high-pressure air enters the combustion chamber, where it's mixed with fuel and ignited. The resulting explosion generates a high-pressure gas that rushes towards the turbine. As this gas passes through the turbine, it spins the blades, which in turn power the compressor. This is the genius of the turbojet engine. It uses some of its power to drive the compressor, making the entire process self-sustaining. The remaining high-pressure gas is then expelled through the nozzle, creating a forceful thrust in the opposite direction. This is the very essence of Newton's third law. For every action, there's an equal and opposite reaction. The rapid expulsion of gas propels the aircraft forward, allowing it to soar through the skies. But these engines didn't just appear out of thin air. They're the result of years of experimentation and innovation by pioneering engineers. In the heart of the 20th century, 2 men independently and simultaneously made significant strides in jet engine technology: Hans von Ohain in Germany and Frank Whittle in England. Their groundbreaking work set the stage for the turbojet engines we see today, powering everything from commercial airliners to military jets. Turbojet engines set the stage for modern aviation, but they were just the beginning. Turbofans, an evolutionary step up from turbojets, brought a new level of efficiency to air travel. If you've ever flown on a commercial airliner, you've most likely been powered by a turbofan engine. But what sets them apart from their predecessor, the turbojet? The answer lies in the term high bypass. This refers to the way a turbofan engine takes a portion of the air sucked in by the front fan and bypasses it around the engine core, instead of pushing it all through. The bypassed air, which is not involved in combustion, is used to create additional thrust. Picture this. A turbofan is like a turbojet engine with a giant fan attached to the front. The fan's primary function is to pull in and accelerate a large volume of air. This air is split into two streams. One stream passes through the engine core, where it is compressed, heated, and expelled to generate thrust. The other stream bypasses the core, flowing around it in a duct and exiting the back of the engine, contributing to the overall thrust. Now you might be asking, why is this important? Here's why. This bypass of air greatly improves the engine's fuel efficiency. The more air that bypasses the engine core relative to the air that passes through it, the higher the engine's bypass ratio. And a higher bypass ratio means better fuel efficiency. This is where turbofans truly shine. They have a high bypass ratio, which allows them to deliver the same thrust as turbojets, but with significantly less fuel consumption. This was a game changer for long-distance air travel, making it more economical and accessible to the masses. But that's not all. The bypassed air also acts as an insulator, reducing the noise generated by the engines. This makes turbofan engines not only more efficient but also quieter than their turbojet counterparts. Turbofans brought a new era in aviation, but the journey of innovation didn't stop there. In the quest for speed and efficiency, engineers developed engines that defy the ordinary. Meet the Ramjets and Scramjets. These engines represent a leap beyond the conventional, heralding a new era in jet propulsion. Let's start with Ramjets. These engines take a different approach to compression. Instead of using mechanical compressors, they use the vehicle's speed to compress the incoming air before it enters the combustion chamber. This method, known as ram compression, is why they're called Ramjets. But there's a catch. Ramjets require a high-speed airflow to function efficiently, making them ideal for high-speed applications, but not so much for slower speeds or stationary starts. This is where their cousins, the Scramjets, come into play. Scramjets, short for supersonic combustion ramjets, take the concept of Ramjets one step further. Unlike ramjets, which slow the incoming air to subsonic speeds for combustion, Scramjets allow the air to pass through at supersonic speeds. This allows for more efficient combustion at incredibly high speeds, opening up possibilities for hypersonic flight and even space planes. But remember, these engines are not without their challenges. The very conditions that make them efficient also make them difficult to design and operate. Imagine trying to light a match in a hurricane, and you get a sense of the challenges involved in igniting fuel in a scramjet's combustion chamber. These engines represent the cutting edge of jet propulsion, each with their unique strengths and challenges. They showcase the ingenuity and innovative spirit of engineers, ever pushing the boundaries of what's possible. Jet engines have come a long way, pushing the boundaries of what's possible in aviation. Jet engines, more than just machines, have transformed the way we travel. The hum of a turbofan engine has become synonymous with the thrill of departure, the anticipation of an adventure. These powerhouses have made the world smaller, bringing continents closer together and making global connection a daily reality. The impact of jet engines on air travel is undeniable. Their evolution from the turbojet's raw power to the turbofan's fuel efficiency has revolutionized long-haul flights. High-speed pursuits are now possible thanks to the likes of Ramjets and Scramjets. But what does the future hold? The horizon is bright with promising advancements. Electric propulsion, an eco-friendly alternative, is gaining traction. It aims to reduce the carbon footprint of air travel, making our skies cleaner. Blended wing designs, another frontier, promise more efficient aerodynamics. These could reshape our aircraft, making them even more fuel efficient and capable of carrying more passengers or cargo. As we look to the skies, one thing is clear: the journey of jet engines is far from over.